You've signed up for Speak Like a Mathematician, so I've got to be really careful that I get everything right, because this is possibly the most pedantic 90 minutes you're ever going to get involved with. I found it really interesting to put together, and I'm going to give you a whole story where it came from and the research behind it as well. Let's look at this starter. This is the same cube seen from 3 different positions, which faces are opposite to each other. Some of you may recognize this as a Don Stewart task. My short tribute to him. He passed away this week. What a brilliant website he's put together. And so many of us will have used it over the years. And a superb website, just a really good mathematical thinking website. I was lucky enough to meet him this year. And so I thought I'd start with one of his problems. Those, I believe, are the answers. I did check with other people. That was one thing about Don's website. You always have to do the work yourself. But I hope those are the answers anyway, to keep you, hopefully keep you entertained. So good morning, let's get started. Thank you for tuning in. My name is Tom Manners. There's my Twitter handle and my email address. That's what I look like when it's not locked down and I'm not trying to cut my own hair. I think we've all got the lockdown face and different hair at the moment, haven't we? But hopefully we're all keeping well. So let's tell you a little bit about me. For the National Centre of Excellence in Teaching of Mathematics, I'm a professional development lead. And it's through my work through the NCTM that I've really started to investigate more ideas as to how mathematics teaching can work. But also, in this last year, I joined Arthur Terry School in the West Midlands, and I am a PGCE tutor. So I get to mark assignments, I get to do research and read research, and it's really keeping me, I think it's fascinating. We're so lucky at the moment that people are sharing so much stuff on Twitter and online for free. There's so much good research out there at the moment, and I'm spending a good amount of time looking into that. I used to be leadership in schools, but I'm enjoying taking this time just to reflect on pedagogy. So what do? 2 days a week I work for myself. I get invited into schools to be a consultant maybe, or just support and CPD. But part of that time is working with the NCTM, and I am a teaching for mastery specialist. I put mastery in inverted commas. And if you want to see why I put it in inverted commas, look at some of my previous videos. My first video about teaching for mastery. It's not a word I particularly like, but I do enjoy the debates we have through the maths hubs. If you know nothing about the Maths Hubs, well, I'm going to make sure I reference this every session that I do. Join the mailing list for your local Maths Hub. Go onto that website, mathshubs.org.uk. Go and have a look and just get the emails from them. See what kind of events are going on. They are free. There can often be working groups going on for over a term. And you can often get funding to actually take part in it as well. It has changed my mindset entirely towards maths teaching. And so a lot of what you hear today will be from my influence within the Maths Hub. So I do encourage you to go onto that website a little bit later on. Okay, so a few reminders for today's session. This session is put together by me and based on my thoughts. Doesn't mean it's absolutely, completely and utterly right. I am not representing the Central Maths Hub here as such, because some of my colleagues there might disagree with me, as they might do at Arthur Terry. And I know a few of my department colleagues are listening, and I know how pedantic one of them is in particular, which is great, because I love discussion about what should we be saying in the classroom. It's incredibly important. I love that. I'm not going to pretend I have all the answers, but I like asking questions to make people think. I'll try and give answers to much of what I do today, but sometimes it's just to go away and think, did I say that right? Could I have said it better? And that's the most important thing, I think, when we're telling our pupils what we're explaining to our pupils. I hope you are going to find the ideas interesting and want to use some of them. However, I'm aware that some of them may be contentious, and there's a couple that I'm going to introduce today. When people said them to me, I'm like, nah, rubbish. But I've gone away and thought about it afterwards and thought there might be a point to this. So it should be an interesting session. What I'm really hoping is that you'll find some ideas that you don't like, and then you challenge it and you think, well, do you know what? I'm going to do it in a slightly better way. I hope you challenge yourself throughout, because a lot of these I didn't like when I first heard them, but when I thought about it and I gave it more time, more consideration, and more discussion with my department. And one thing you're going to hear me say a lot today is consistency in your department. What are you all saying and why? So it's the reason I was playing 5 for those of you who tuned in earlier, because slam, dunk to funk, speak like a mathematician. Now, at the moment, I'm working with a few departments on what do we want our Year 7 learners to be. And I want them to speak like a mathematician. I want them to use the proper vocabulary, the proper words. And that complete pedantry, if you want to put it that way, that's what we're focusing on today. That expression, speak like a mathematician, came from the Bolcaris School that I visited in Gloucestershire. They're the lead school for the Glow Maths Hub. Brilliant hub. But that's the title for today, Speak Like a Mathematician. It's not me, but that's my feeling. Do you know, after Christmas, when you've eaten loads and you're feeling a little bit slobby and you're lying around on the sofa, that's where today's talk comes from. because I was lying on my parents' sofa and I was just feeling a little bit, ugh. And I just tweeted. I just got on Twitter, and if you're not on Twitter, it's a great source of debate, sometimes infuriatingly so maybe, but so much good stuff shared. Now, I put this tweet out there. I'm trying to compile a list of things maths teachers should never say, as they can lead to misconceptions, i.e. do the same to the top as you do to the bottom, and when you times by 10, you add a 0. And I asked a few people to retweet it, and I found it really interesting, the response I got. Now, why did I send this tweet? Pupils change teachers in most schools during their school life, don't they? And as I said it already, consistency is surely needed from teacher to teacher within a department. If one person says KFC, then the next person says multiplied by a reciprocal, well, what's the pupil going to do? Surely consistency within your department is incredibly key. And why not use the proper language? That's surely what today's talk's all about. I was intrigued as to what tricks are used and which cause problems later, which I may not have heard of. What kind of things might be taught? I've not taught in a primary school. I've worked with primary school. I'm not taught there. I'm hoping I'll get the chance to soon. But what tricks are used? And it would be interesting to see sometimes what tricks are used in secondary schools as well. And I also sent the tweet because I've got a belief that solely teaching tricks is setting low expectations of the pupil. If we turn around and say the pupil can't do that, they can't use the proper vocabulary, we're immediately setting low expectations, and that's against a belief of mine as a teacher, certainly as a PGCE tutor. So what did I get in response to this tweet? Well, ideas I hadn't previously considered about my choice of words and methods used around the world, and it was around the world because people were tweeting from America and other countries as well. Fantastic. I was really pleased with the response to it. It was really fascinating. I got some links to research papers on similar areas as well, which was a nice response. And what else did I get in response? I had a few more followers, so that was nice. So how's today's session going to work? You're going to see tweets I received, and in some cases the responses and conversation that came about from them. Some examples modelled by me, I've got them ready, in a Blue Peter style, and they're to my left here. I'm going to explore some of them and explore why they may or may not be wrong. I'm going to give you links to research papers. I've got a load of links ready, but what I didn't do is send them producer Adam at the start. So I'm going to copy them into the chat at the very, very end. All the links that I refer to today, I'm going to put in the chat box at the very, very end. But yes, links to research papers discovered and some links to books I've looked at to prepare for today. Additional thoughts are welcome. Do challenge me on the chat function. So Adam, my head of department for Arthur Terry, is producing today. Hi, Adam.
Hello.
Oh, send in questions on that. I can't always, again, I won't necessarily have all the answers, and sometimes hopefully I'll actually give you the answers anyway, well, that I believe. But if you do want to throw some remarks at me, Adam will interrupt me and let me know. Now, today could be interesting. So that was the original tweet. 28,000 people got involved with it by liking or forwarding or remarking, and it was really interesting just to have that response rate. So the National Curriculum's assessment objectives are very important for us, and maybe we don't take enough, we don't consider them enough when we're planning our lessons, because all pupils should be becoming fluent. All pupils should be able to reason mathematically. All pupils should be solving problems, and there's some key expressions there that I want to make sure we're referring to. Using mathematical language, there it is in the National Curriculum. So do we say the top of the fraction, or do we say the numerator? Now, surely by not saying numerator, we are lowering our expectations of our pupils. Just a thought. Now, if we're not using consistent language and using the right language, can we really expect pupils to have a conceptual understanding? And fluency comes before reasoning and problem solving. You need to really be fluent before you can reason well and solve problems. So that fluency, if we're saying we've got to develop conceptual understanding, I think we've got to do it right, and we've got to use that proper language. And again, this is going to be a very, very pedantic 90 minutes. I refer to this in every session I do because it's a brilliant report in how to improve maths in both primary and secondary. And I've got it next to me actually for this next bit, because here are the 8 key recommendations on how to improve maths. And number 8 there, support pupils to make a successful transition between primary and secondary school. A lot of maths hubs actually run sessions on year 5 to 8 continuity. And surely part of that is making sure we're all being consistent in the language we use. But what else is there? Using assessment to build pupils' existing knowledge and understanding. And within the book, I've got it to my left here, addressing misconceptions. It's important that misconceptions are uncovered and addressed. Multiplication makes bigger, for example. If that's what a pupil believes, is that always true? Teaching strategies for solving problems. Teaching pupils to be able to compare different strategies and different methods. Well, if we can't use the proper language, how could they compare them accurately? Teaching pupils to interrogate and use their existing mathematical knowledge. Well, how can we interrogate if we're not using the same language? If someone speaks French with someone speaking German, how can they possibly have a proper interrogation? Enable pupils to develop a rich network of mathematical knowledge. Well, again, choosing between mathematical strategies. And if you can't compare the strategies because you're saying different words, well, how can you possibly do that? And develop pupils' independence and motivation as well through their learning. Well, if you're asking people to discuss independently, maybe. Well, motivation I'm going to come to in a bit because there's really a couple of nice lines in research about that. But be able to speak the proper language makes you feel more intelligent, makes you feel more of a mathematician. Got some research to share on that a little bit later on. So I've used a number of books today, and there's a subchapter in this wonderful book from Mark McCourt. Very, very interesting read. And the subchapter is called Teach Everything Correctly First Time. And I am going to have to read from this, I'm afraid. Approaches to teaching key mathematical ideas were very often sufficient for handling the level of maths that pupils encountered at the end of primary school, but did not hold true or generalize readily for later. Many of the methods pupils are being taught were backward facing, suitable only to take them to a known endpoint, i.e. that year group's endpoint or that class's endpoint, rather than going forward facing approaches to maths that plan for later mathematical ideas. And let me give you an idea. One of the tweets was sent. I always tell my classes that adding a 0 is a secret and get them to whisper it, explaining it's just a helpful little method to multiply by 10. So when we tell the pupil that, what do they think when they come to this multiplication? 3.7 times 10. These are the misconceptions that only have that end point. They don't help the mathematician as we progress all the way through to year 11 and hopefully beyond as well. It's these backward-facing methods often give the pupil a quick win, allowing the pupil to feel comfortable and to perform, but seriously hinder the pupil later when they're faced with a problem that requires a proper understanding of an approach. And it's that I'm going to be asking you to think about continually today. Getting it right in that lesson. Yes, there's a feeling as a teacher that we want to get it right in that lesson, but we want them to get it right next year as well and remember it and have that conceptual understanding. We can tick the box today and yes, they remember they got it right today, but does that mean they've learned it? These are two fabulous books, the one on the right, especially designed for primary, one on the left there, especially designed for secondary, both by Dr. Dougherty, who works with the Art of Maths Mastery format. And one of the pillars of their format of mastery is language and communication. They both cited this same paper, and this is the one that I was referring to about pupils using the right language, a paper from Clairley in 1998. Becoming able to articulate mathematical ideas, concepts, and reasoning has a profound effect on the way that pupils see themselves. They see themselves as a mathematician if they're saying the right things in the right way. It's a positive response in the classroom. So are you ready? And because I had an Austin Powers picture before, I've got to have another one. I thought I found this one. Are you ready to do some work? I would suggest you have a piece of paper now next to you and just write down the occasional word and look back at it later, because there's going to be some words I refer to, and then you'll think back and think, should I be saying that? Feel free to argue with me as the session goes on. As it goes on, I'm going to keep producing tweets that I was got sent and my responses to them. So let's go. Taryn points out, calling a rhombus a diamond. A diamond is not a mathematical shape, people. Let's just call it a rhombus from the start and get on with it. Maybe those people who play cards should start saying, I've got 5 of rhombuses here. That would be nice. Or is it rhombi? I don't know. I'm really pedantic about the things I say. But it's a rhombus, it's not a diamond. Referring to a sphere as a fancy circle. True story. And I'm smiling at the moment because one of my departments sent me a message this week about how his wife used such language as this, and he was incredibly disappointed. In fact, the same teacher sent out a year 12 pupil for calling a rhombus a diamond. But how do you describe a sphere? It's not a 3D version of a circle. So one of the things I often encourage is the use of the NCTM glossary. You can get this for free. Just type in those words onto Google, and it's a glossary for teachers to be able to use the same language. And to help ensure common language, I put a question mark there, and you'll see why in just a few moments, because I do encourage you to use this. I absolutely do. But there are times that you might think it's not quite right. For example, a sphere is a closed surface in 3-dimensional space consisting of all the points that are a given distance from a fixed point. Okay, some people might not like that language, think it's a little bit complicated. So I went to maths is fun. Math is fun. And it said a 3-dimensional object shaped like a ball. I like that. But look at the consistency between the two definitions here. every point on the surface is the same distance from the center. So if I was in the absolute center of that sphere on the left-hand side there, everything on the outside, every point of it is the same distance to that center. And of course, the same exists with the rules of a circle. The rule of a circle is every point on the outside is the same distance to the middle. And that really helps with loci, of course. A circle isn't round, because if it was round, an oval would be a circle, because oval has round bits too, doesn't it? Just something to think about. What we got next? Oh, D.R. Wilson, thank you. Enlargement means gets bigger. If we say those words, is it always true? Let's look up enlargement. A transformation of the plane in which lengths are multiplied whilst directions and angles are preserved. Ugh. This is why sometimes using the NCTM glossary might not quite be right. All right, I've gotten cross. There's an Austin Powers theme running through the first 10 minutes of this. So let's go. What else could I say? Because enlargement means gets bigger. I went to math is fun again. Oh, that's the final Austin Powers moment. Silence. It does not mean get bigger. Why is this a problem, of course? Well, there's this kind of example. We ask pupils to do fractional enlargements when it comes to GCSE maths. And when a shape is enlarged by a scale factor between 0 and 1, the image is in fact smaller than the original shape. Does anyone remember those videos? Like, oh, what were they called? And this is why you prepare every single word when you do a talk. I remember seeing Ben Shepherd present one of them. And it showed an example of how this image, a photo, is in fact an enlargement. So here's taking a photo of me, and then there's a photo of me here, and it is an enlargement. It's just smaller. So what can we say about enlargement? I found this citation, not citation, the definition from bestmaths.net. An enlargement is the transformation where an object maps to an image of the same shape but different size. The object and the image, object, image, something we use when we're saying about the first shape and the second shape, are said to be similar. They're in the same proportions. An enlargement requires a center of enlargement and a scale factor. Not always necessarily about the center of enlargement, but certainly when we're drawing it. But yes, those two shapes are said to be similar. An enlargement does not always mean get bigger. What else do we often say? Minus to describe a number less than 0. Minus and minus make a plus. But Tim argues this is common usage in real life. The temperature was -2 overnight. Oh dear, we need to connect it to -2. No, we don't. I argued this one straight away. Real life needs to change, people. And I am going to fight the BBC one day. I'm going to fight the Met Office. Let's start the revolution. When it gets to minus temperatures overnight, it's negative. It's negative. It's positive temperatures and negative temperatures. And if you're passionate about integers, I've already done a video on this. I'm going to refer to it in a few moments. Anything that isn't true, let's talk more about these negatives and minuses and subtracting. Telling people, primary children, you can't do 3 take away 5, can't you? You can't do 6 take away 8. As soon as you've told them you can't do it, we've got a problem there, because you can do it. And that's an example of what Mark McCourt said. If we're telling them it's okay, you can't do it, and I've passed year 2 maths, year 3 maths, whatever it might have been, well, you're not helping year 7, 8, 9, 10 maths. It's a tricky one, says Claire. She's right, because there is a cognitive load involved. And that's the challenge that the primary practitioners have got to overcome. Because you're saying, well, can you do it? But it involves negative numbers. What would you do? And Claire's quite quick answer is, well, maybe we can't do that yet. And that's just very different language. And that's really quite powerful, because we will be able to do it one day. At some point, not a maths teacher shared this, 2 negatives make a positive. There's a lot of thoughts about this, about negatives and positives and minuses and subtracting. We're going to come back to what she says about formula triangle in just a few moments. They do diddly squat for learning and understanding. 2 negatives make a positive. Yes, you can see lots of people referring to this. Negative and positive, they're a state. It's an adjective describing the noun. Minus subtracting is an operation. So for take away -2, I can take away 2 negatives. Now, if you are interested in this, oddly enough, it keeps coming up on Twitter, and Watson was arguing about this last week. Fantastic. All of the emails I send out tend to give links to the previous sessions. I'm not going to answer any questions on integers today, because there's a good hour devoted to it on a session. I think I did it last week. So please do watch my previous session on integers and representation. I really enjoyed putting that one together. But we're not going to focus anymore on negatives and negatives, positives. But there's the difference for me. Negative, positive are describing the state of the noun, the adjective. Minus, take away, subtract, they are an action that we can perform. So formula triangles are made, and Karen pointed out, and so did D-Maths. Formula triangles, well, they make Karen shriek when pupils use them. But loads of us use these. Loads of us use formula triangles. What's wrong with those, apparently? Now this one, Michael Pershing. Now this person's been interviewed by Craig Barton, and I was like, wow, this is like a really famous mathematician getting involved with my tweets. I'm really excited. But what he linked me to something, nixthetricks.com. Karen also told me to go to nixthetricks.com, and I was like, what is nixthetricks.com? So I went to go and have a look, and this is where it really became interesting to me when people were sharing some of these stuff I'd never come across before. So let's look at Nix the Tricks. Now they said the formula triangle. To find distance, bearing in mind, by the way, I know that in England we tend to use speed distance time, but they're using rate here. Now, why is this a problem? Let's have a look at it. Covering up part of a triangle is not a valid method for solving an equation. Direct variation problems are no different than any other equation. Let's have a look at the fix. It is perfectly reasonable to expect students to learn one equation. Let's say distance equals speed times time, or rate times time, which is no harder to remember than the triangle. That's very, very, very true. Once they know one equation, they can use opposite operations to manipulate it. Now, for those of you who teach Key Stage 5, we don't always have to remember all the trig identities. Remembering one or two and then be able to derive the rest is really important. But that's actually very important for all learners of maths. Let's look at some of the research behind it. There's actually been a new video on this being put out in the last couple of weeks, and I've got to sit down and watch it. But low attainment in maths, an investigation of Year 9 students. Things which make a big difference to low attainers are the number lines and arrays, and again, I've looked at those in some of my previous sessions on representation, but the one estimation, I'm going to refer to that later, but derived facts. These are really important to making connections in maths, so we have conceptual understanding that 7 times 8 equals 56 actually is a connection to 56 divided by 7 equals 8. Students rarely use derived facts and rarely estimate, and teachers do not teach these explicitly. We do not make these connections enough between division and multiplication, for example. And even this example with formula triangles, speed equals distance over, hold on, have I said that right? Speed equals distance over time. Well, therefore, distance equals speed times time. Teachers think derived facts are obvious, but they're not. We need to make them explicit in our lessons and make connections in maths. And when we're making connections, we're doing something really powerful with the synapses and the different regions. If it's something you recall from earlier on, I think it's a Willingham quote, learning is just remembering in disguise. If we're learning something that we can link to something we've done before, then we're making those connections, which is really, really powerful. Ooh, the first time I heard this, I thought, well, what's wrong with BidMaths? Don't you be mean. That's it, just BidMaths, says Mr. Mattock. He's one of the teaching for mastery specialists of the Maths Hubs as well. He's written a great book, which I'm going to be using in just a few moments. Anything to do with BidMaths, BODMaths, GEMS, GEMMA, I'm going to talk about in a minute, PEMDAS, or any such complete and utter nonsense. Look at the passion. Look, once you say, well, hold on a second. Well, I shared I was interested in this because I've not really thought about the replacement yet. And I've said here I've seen a pack of pens analogy, and that's where I'm going to go to my, my camera. And here's my pack of pens. Here's one I prepared earlier. Imagine I had 6 pens. Here they are, just over here. And I bought 4 packs of 10 pens. Does that mean I have 6 plus 4 lots of 10? So 10 lots of 10 is 100. Because that's what it says. I had 6 pens and I then bought 4 packs of 10 pens. 6 plus 4 is 10. And that's where the argument then comes back. So let's go back to see what he's got to say about it. It should be replaced with proper knowledge of how operations work, including the laws of arithmetic. So not this acronym that we just learn BidMaths. We understand BidMaths. That's interesting. So let's have a look at his book, 2019. Given I'm such a big fan of representation, this is a really, really, really good book. Calculations where order is important, and this is a similar example of what I've just done there. We've got 4 times 3, so can you see here, you've got 4 lots of 3, then add a 5. Well, if I change the order of what I've written, 5 plus 4 times 3, does that do the same? 5 plus 4 is 9, isn't it? Times 3, so here's a 5 and a 4. Can you see that there? 5 and a 4, and I've got it 3 times. They don't seem to equal each other. See it another way. 4 squared plus 3 does not equal 3 plus 4 squared. Here we go. We've got 4 squared here, plus 3. Then 3 plus 4, 7 squared. We can see they don't equal each other. So what Pete is vehemently arguing is that, do we have to understand that? Well, we do have to understand BidMaths, not just use BidMaths. Once again, another way of putting that one, 4 squared times 3, 3 lots of 4 squared, 3 lots of 4 squared, 3 times 4 is 12. Really interesting to show that representation so pupils understand where it's coming from, not just repeating BIDMAS because of BIDMAS. So we went to Nix the Tricks to see what they had to say about it, and their fix here: students should know that mathematicians needed a standard order of operations for consistency. And doesn't this slide show that? For consistency, doesn't this slide show that as well? We need the order of operations for consistency. It's not a rule, BIDMAS. It's something we need to be able to do maths together. The most powerful operation should be completed first. Exponential, this is really interesting. I never thought of it until I read it on this Nix the Tricks. The most powerful operation should be completed first. Exponential increases or decreases at a much greater rate than multiplying, which increases or decreases at a greater rate than addition. What an interesting line. Really hadn't thought about it until looking at Nix the Tricks. I thought that was really interesting. Now, Nix the Tricks, oddly enough, suggests Gemma. So they're grouped together. Of course, Mr. Mattock would disagree, but they're saying the grouping is better. Parentheses goes together. Exponentials and then multiplication, division is implied, of course, because derived facts, multiplication and division, they're connected. And addition is subtracted. Subtraction is implied because they're connected. So that's interesting as well. Keep flip change. We'll come up to that in a second. Let's talk about that bus stop first. Let's go to my camera again. Here is the bus stop. Well, if we're making those connections in mathematics, well, why don't we realize that bus stop, short division from now on, please. Short division is just related to multiplication. 7 times what is 56? You have those arrays in year 7 and year 3. And we start making that connection now, that what is the number that I multiply by 7 to get to 56? And suddenly short division, we've made that that link between multiplication, because area of a rectangle, 7 times what is 56. The bus stop is not useful to anybody in any way at all. And I am unanimous in that. Quote from a 70s comedy show for you there. Irene Stone thought the same. What are we doing when dividing by a fraction? Turn upside down and multiply. Top by top, bottom by bottom. What? What are we doing? This was only a tweet a few days ago, but I am loving this tweet from Gary Lamb. If I, as a student, am carrying out an algorithm based on someone else's awareness rather than on my own, then how do I recreate it? What to do if I forget or misremember the algorithm? If I misremember the algorithm because I haven't understood it, I'm just following a pattern. That's interesting. If an algorithm is not based on my own awareness, then I cannot recreate it. So if I forget or misremember, then I'm stuck. And this reminded me of the wonderful Craig Barton, his awesome podcast. He did a podcast with Jane Jones, formerly the HMI Ofsted lead for maths. And she pointed out there are too many rules in mathematics to remember. We can't expect pupils to be able to remember all these algorithms. We're teaching for understanding. It's well worth listening to that. It's a really good, certainly for heads of department, and for all maths teachers, matter of fact, a really good podcast, that one. There are too many rules. If you misremember the rule, you're stuck. You're stuffed. But if you made connections, well, do you know what? You've got a chance. So I went to Nix the Tricks to see what they were saying. Let's have a look. Now, the first thing they said is some people say this idea of cross multiplication. Well, do you mean cross, like diagonal, or do you mean across? So which one do you mean? I'm confused. Well, look at this expression here. Ours is not to reason why, just invert and multiply. Yay! Let's carry on. The fix that they're referring to, use the phrase multiply by the reciprocal, but only after students understand where this algorithm comes from. The reciprocal is the precise term that reminds students why we're switching the operation. And I'm going to go through these a little bit step by step as well, because there's another alternative to using KFC or multiplied by reciprocal, and I really liked this, and I thought it would be worth talking through. How many 2/3 go into 2/3? Well, it's 1. That's easy. We understand that. 2/3 divided by 1/3. Well, how many 1/3 are there in 2/3? And hopefully we'd be able to make sense that there's a third and there's another third. There's 2/3. Oh, there's 2 of them. Let's carry on. This is not as obvious, but what is 4/5 divided by 3/5? It says it's 4/3. Let's go to the one I prepared earlier. So then, I have done a little bar model here, and I've got 4/5 and I've got 3/5. And there's one lot of 3/5 here, and I can see one lot there. So I've got one lot of 3/5. But I've also, I mean, there are 3 parts to this, and I've got one more part. And this one is 1/3 of this whole. So when I've done 4/5 divided by 3/5, I've got 1 1/3, or 4/3. 4/3. And using the language I've been trying to use there, I've got 1 1/3 lots of 3/5 in 4/5. Now, lots, we often say that would be multiplication, and we're going to come to that connection in a second. 4/5, therefore, divided by 3/5 is 1 1/3. So hold on, 4/3 times by 3/5, what does it equal? I've done that smaller, but I apologize. Equals 12/15. 4/5. Look at the connections going on. It's the same with this. 56 divided by 8 equals 7. There are 7 lots of 8 in 56. Really interesting when the denominator is the same. Let's go back to it. What about this one? 4/5 divided by 1/2. Well, what about if we, what a graphic. I'm sure you're impressed by that motion there on PowerPoint. What about if we do it like this? What about if we make the denominators the same? That makes sense, given what we just did about 4/5 divided by 3/5. 8/10 divided by 5/10. It now makes some sense. And of course, when we add and subtract fractions, we get the denominators the same. What an interesting way of possibly teaching division of fractions. Let's carry on. Seamus says, well, I don't like it when people refer to any calculation other than addition as a sum, rather than a question or a calculation. 21 likes on that one. Rachel says, doing a sum rather than calculation or other alternatives. Sum means finding a total. I thought that was interesting. So I thought, well, let's look up sum. So I went to the maths glossary because I do use it a lot. Just because sometimes the language is a little bit complicated, I certainly still do use it a lot. Sum, the result of one or more additions. There you go, it's now put down for me. But I noticed just below sum was supplementary angles, and I noticed the word there, look at that. 2 neighbouring angles whose sum is 180, reminding me that it's all about addition. So sum is to do with additions. That's really interesting. Mark Walker, when subtracting, and by the way, I don't think I've said it enough yet, this was just put out as a tweet just after Christmas, and I want to make sure I have actually said thank you to everybody who responded to this, because it made a really interesting session for my PGC students, and I'm not going to lie, I'm hoping you're finding it interesting today. So Mark Walker did tweet and say, when subtracting, the biggest number goes on top. So we can't do 7 take away 10. How do we do that? Is that always true? Is that right? How often? Now, those primary teachers who are really looking at teaching for mastery, whether it be through the NCTM, whether you're using Singapore Maths, whether you're using Maths No Problem, you're using the proper language. Secondary colleagues who are listening today, how often do you say the minuend take away the subtrahend equals the difference? Now, if the primary schools are doing this more and more, secondary teachers, shouldn't we be doing exactly the same? The number take away the other number. Which one? I'm confused, sir. Minuend take away the subtrahend equals the difference. And so I thought, well, let's go a little bit further into this. 2 numbers multiply to make a product. 2 numbers add, the 2 addends make a sum. 2 factors make a product. And then we're making connections elsewhere in maths when we're talking about factorizing, because the 2 factors multiply together to make a product. Look at that one at the bottom. Divisor, quotient, and dividend. I'm going to come back to it in a second, actually. But product divided by a factor will give us another factor. When multiplying the number, it always gets bigger. Does it? When we multiply, it always gets bigger. Does it? There's your example. If we say this, when dividing, the quotient is always smaller. Really? We know how common 6 divided by 1/2, how common it is that the pupils will tell us the answer is 3. Because have we used this concept? Have we used these misconceptions, these sentences that aren't always true? When we've said multiplying means get bigger, dividing means get smaller. Again, we go back to what Mark McCourt said at the start of the presentation here. If we're teaching those facts that exist in the year 3 maths, but not in the year 6 maths, they're disproved and they're not true in year 6, we're limiting the capacity, we're limiting their progress in maths. And I know some of you will be responding with the pressure that we've got in teaching. Don't get me wrong, I completely get it. That we've got to understand, we've got to get our kids through certain stages. But I like the name of the chapter that Mark McCourt's, just teach everything correctly first time. And I'm going to use a quote at the very end, and I can cite part of it now, along the lines of, making sure, well, I'll get to the quote later on, but the point is we've got to assist our mathematicians to progress through all the to year 11 and hopefully beyond, not just the year they are currently in. I mentioned that word quotient. Now, I haven't used quotient, the word quotient when I was teaching secondary maths. I'm teaching it less often now, of course, but I didn't use the word quotient until I was doing Key Stage 5. And look at that, it's being used in Key Stage 2. The divisor, how many times the divisor goes into the dividend. The result is the quotient. How funny that we don't. And apologies for those secondary colleagues if you're arguing right now saying, I do use that, then brilliant. You're doing it right. Let us carry on. What else we got? Oh, Karen told me to go and look at Nick the Tricks as well. But she came up with this. My current avoid is saying cancel. Instead, I say divide away the common factor. So 36 divided by 48 or 36 over 48. That's interesting because Karen thought, well, what about if you're actually cancelling common factors? Well, I think she's got a good point, hasn't she? So let's go and see what's got to be said about this one. So 20 divided by 30 or 20 over 30. Well, if we cancel down, what do we do? Are we just cancelling the zeros? Does that work, for example, for 25 over 35? Do you cancel the 5s? Do you get rid of the 5s? Or we're actually dividing down. Now, if I've rewritten 20 over 30 as 2 over 10 by 3, divided by 3 over 10, am I cancelling the 10s? Am I dividing both the numerator and the denominator by 10? And that's what I've chosen to perform here. And there I've got 2 over 3. Now, you say you cancel out there, but is that a mathematical word? Today, very much, as you've probably got already, is about being pedantic. That's not right. It's about being right. I've said being pedantic quite often, but it's not about that. It's about saying things mathematically correct. And strictly speaking, accurately, we are dividing the numerator and the denominator by 10. That's how we are simplifying our fraction, not reducing our fraction. I'll come to that. And those are the words there talking about cancel. Cancel is like a magical thing. I like that. Cancel is like a magical thing where divide communicates the math we're performing. Admittedly, I'm overlooking the word math. But you know that's a transatlantic thing. For me, it's about using the mathematical language and ensuring the students are using the right mathematical language. I think Karen and I would get on very, very well. Let's go. What have we got next? You can't divide 5 by 2, can't you? You can't divide 5 by 2. In fact, I'm gonna go off my script here. I'm going to show you something that I do in class. You can't divide 5 by 2, apparently. I tell pupils I can divide any 2 numbers in the world. And they're like, no, you can't. So I can. I can divide any 2 numbers. Give me a proper number. Give me a big number. Come on, give me something special. And they'll say 23. And I'm like, that's not big. Give me a bigger number. Come on, give me a bigger number. And they might say 482. I'm like, come on, give me a bigger number. And eventually they'll say, I'm not going to do the Priti Patel number. I'm going to do 2,374,976. I'm going to go for that. I can divide that by any number. Give me a number. Now, admittedly, I'm hoping they'll give me an integer to make life easy, and then I don't have to have the argument about fractions. But if they give me 72, brilliant. I have now divided them. That is a number. I have created the number that happens when I've got 2,374,976 divided by 72. I have given a number answer. And do you know when, certainly for those of you who teach Key Stage 4, when you're doing GCSE and you're worried about the kids turn around and say 7 over 2, so x equals 7 over 2. Oh, I've now got to work out what that is. No, you don't. That's a number. There's nothing wrong with that answer. If they can change that to 2.5, sadly, they're not going to get the marks. And it's this idea that this thing here is a number. And that's why we need to be communicating with primary and secondary all together sometimes. Because are we all being consistent about it? There's nothing wrong with 7 over 2 as an answer. It is a number. Let's carry on. You can't divide by 2. Naomi, I love her, she's brilliant. Only even numbers can be divided by 2. My 8-year-old came home, was adamant this was correct. Anything can be divided by 2, can't they? Now, this is where I piped up. It's been mentioned that the word divisible changes this, and that's very, very true. Only even numbers are divisible by 2 is true. I never really thought about it before, but I can't stand it when I hear that sentence, you can't divide by 2. Yes, you can. It just doesn't give you an integer answer. Ooh, a prime number is only divisible by itself and 1. Now, prime numbers. Now, this is where the definition of prime numbers can be very succinct, and we can make it very clear. And linking back to some of the language we used earlier on. Tom said it. It's correct, isn't it? Oh, Mr. Ducky didn't like that. No, with an exclamation mark. 1 is not prime. However, it is divisible by itself and 1. The correct definition of a prime number is it only has 2 factors. I looked at this in my presentations in the last few weeks as well. The correct definition of a prime number only has 2 factors. 2, ooh, Mr. Martin gets in there again. Get in there, son. 2 distinct factors. Exactly 2 distinct factors. Super stuff. I really like that. Sandy, that a rectangle has 2 long sides and 2 short sides. Or no, that's a square, not a rectangle. Obviously an American tweet, but let's look at rectangle on the NCTM glossary. It's a parallelogram. A rectangle is a parallelogram with interior angles. I think we can assume if you've got 1, you've got the rest. Opposite sides are equal. If adjacent sides are also equal, the rectangle is a square. So let's make this clear. A square is a type of rectangle. It's a subset. All these rectangles here, square is inside. If the adjacent sides are not equal, the rectangle is sometimes referred to as an oblong. Ooh. Now, for years, I just thought oblong, it's like gambol. I thought, you know, Birmingham is I'm from Birmingham. Gambol is a Birmingham word, a Brummagem word for forward roll. And I always thought oblong was a Birmingham word for rectangle until I started really kind of looking this up and teaching. A square is a special type of rectangle. The use of the word oblong resolves this issue. There it is, the fix. If the adjacent sides are not the same length, then use the word oblong. An oblong is a rectangle which is not square. Wow, love it. Really enjoy that. Let's look at square, by the way. A quadrilateral with 4 equal sides and 4 right angles. The rest of it's about the number and square numbers, so I'm not going to look at that quite now. This is a really good website. Good old Craig Barton gave us another one, mathsvens.com. Imagine, where do you put a rectangle in the subset? Where do you put a square in the rectangle subset? It's that real conversation. Where would you put a parallelogram? Because a rectangle is a type of parallelogram. Go on to Mathsvens, really good website to get some good conversation about that. Here we go again. Foil. I really like this tweet because it just says it. Foil. Now, Karen was kind of concerned about this. Isn't FOIL an acronym that is merely used to help everyone write terms in the same order as everyone else and hence make it easier to spot mistakes? Also very useful when it comes to factorizing by inspection. Well, Mr. Matter, again, I get on with him. There are 2 things. Does the order of the term matter? No, the order of the terms doesn't matter. We're drawing attention to a surface idea rather than the deeper mathematical idea. Now I'm going to do an example of this in just a few moments. FOIL only applies to the product of 2 binomials and therefore lacks usefulness for exploring the concept of expansion more widely. Let's have a look at this one. So I've got it here. This would be an example of where you might use FOIL, x plus 3 times x plus 7. But can you use FOIL for that one? The answer, I'm afraid, is no, you can't. And if a pupil looks at them, they haven't got any idea of what all this means, and they go, FOIL, then we don't know what's happening. Let's have a look at an example of where this comes from. They'd be practicing this, just the one term outside the bracket, so x lots of x plus 7. There it is, so x times x and x times 7. And you can do some brilliant stuff with algebra tiles with that. And again, look back on my previous videos. Then 3 lots of x plus 7 as well. So 3 lots of x and 3 lots of 7. You can really represent that and visualize it superbly. But I've got x lots of x plus 7 plus 3 lots of x plus 7. Now, given the fact that the bracket is the same, therefore, I've got x plus 3 lots of x plus 7. And by making these connections, FOIL isn't needed anymore because I've got x lots of x plus 7, i.e. redo this bit. And I've got 3 lots of x plus 7, i.e. redo this bit, the stuff that I previously learned. Making connections, so important in maths. It's an interconnected subject. It says it very clearly in the national curriculum because it's true. Let us carry on. What's this one say? Borrowing rather than exchanging. I don't plan to give it back. I like that. But, you know, nice intent there, brings some humanity to maths, but it's true. We don't borrow, we exchange. Always start in the ones column, says Simon. Lovely guy, Simon. With adding and subtracting column method could lead to misconceptions when decimal arrives. So what do you do when it's 3.2 plus 4.7? Do you start with the 3 and the 4? You don't start in the ones column, do you? At least he said ones. I piped up here. Ooh, 4 likes, isn't that nice? Always is a strong word, isn't it? Although it's great when used as part of an always, sometimes, never. So even you could go back to that. Do you always start in the ones column and have the discussion in the classroom and the pupils will identify, no. We look for what maybe the smallest, I want to say smallest unit, smallest column. Ooh, I don't know what they'd say there. That's interesting. Have a think about that. The decimal moves. I went through a spell where I was adamant that this isn't true. How dare anyone say the decimal moves? How dare they? Colin Foster's written something interesting on this. Ben Gordon, and I keep showing some of these, and I'm showing some of them in particular because I want you to follow some of these people. And Mr. Gordon is fantastic. I'm using some of his stuff later on in the presentation. But Colin Foster says this doesn't matter about the decimal moves, and he wrote a paper on it. And again, I'll put the link at the end of the presentation today. Can I just move the decimal point? And I'm still not sure. But this is where you have that conversation, and because of the format of today, we can't really have decent conversation, but I encourage you to have a conversation with your department to go and discuss, what are we going to say? What are we going to say in this school? When they move from me in year 7 to you in year 8, are we going to be consistent? Does this easiness of saying the decimal point come at the cost of understanding? He says, I'm not sure it does. On the face of it, this would appear to be a case of relative motion. The decimal point and column headings moving to the right is exactly equivalent to and indistinguishable from the digits moving to the left. Now, I like this line here. What matters is the relative position of digits and the decimal point, surely. Now, he talks about how easy it is on a interactive whiteboard to move the numbers, but is it really easy with paper as well? So, does it really matter? Just being consistent, discuss it with your teams. What have we got next? I'm afraid my mind only said one thing straight away. It does. It just sounds dodgy. Still, when something goes through the magic tunnel, the equal sign, it changes sign. Oh, yes, the magic tunnel. I think my first lesson I ever taught. And I don't want to speak ill of the teacher on my PGC year, but still, I was teaching this exact topic. And she was adamant afterwards. She said, I was so close to stopping you teaching. How dare you teach them the proper mathematics? We don't teach them the proper mathematics here. We do the moves over the magic wall and becomes a -2. I was like, oh, good God, I'm going to be in the right profession here because I'm going to do it right. Through the magic tunnel, isn't that nice? The 2 squeezes through the tunnel and it becomes a negative. Change sign, change side. Are we teaching them maths or are we teaching them tricks? Ooh, Rachel's back. Thank you, Rachel. I like this one. The crocodile greater than less than symbols. So unhelpful. Now, interesting, because people would argue with this one. Now, Ray agrees. I still shudder when I hear this. I have emotional scars from being taught this at primary. It made no sense. Sarah actually said, you know what, I think the pupils find this easy because they use inequality signs. The hungry crocodile eats the bigger one. This is the point I like from Rachel. I relate to maths, Ray. I was never able to remember which way round the crocodile was supposed to be. And I've got to say this, I teach numerous secondary pupils who do not remember which way it's supposed to be. Look at that more helpful representation there. 4 fits inside 1. 4 is greater than 1. We've seen that from Shanghai lessons when we're doing these exchanges through the maths hubs. And what a powerful representation there that then has a conceptual understanding, can be linked to understanding. However, Rihanna's a really good point, very good point. What about negatives? Now, this is where I piped up. Not every representation suits every situation. Having introduced the larger, smaller than, I should have said greater than actually there, shouldn't I? Using the images above, you can then transition onto a number line as a visual way of representing the position of negatives. And I think I should probably go onto the camera for that. So if we've got 0, we'd have used that representation before. That was seen before with this thing. And we can see 3 is greater than 1. And we can see 3 is over here, is on the right-hand side of the number line. So when I'm going to number -1, -2, -3, the right representation for the right situation, which is the greater number, 3 or -4? Well, the question is, which is further along the number line here, and which is further along? It's 3, isn't it? So 3 is greater. That would be hard to represent in this format. So the keywords I want to use here, and I'm just going to make sure they're on screen again. Not every representation suits every situation. And we keep on going. Half base times height. Books usually show the base as the horizontal. Yeah, so I actually just typed in area of a triangle, and these were some of the first questions that came up. And look at that, all the bases at the bottom. At the bottom. Moving on. What about this one? What are the pupils supposed to do here? Show bases horizontal. But sir, but miss, I don't know what I'm doing now. What's on the base? What's on the bottom? What about this one? What's the pupil going to do if they've been taught that the area of a triangle is half base times height? What are they going to do with that one? With that in mind, of course, times them together and divide by 2. Thank you, Alex. Alex is a lovely guy. Which 2 do we times together? Is it 10 times 5? Is it 14 times 5? Is it 10 times 4? It's all about conceptual understanding, everybody. Let's keep going. Start my teacher. Area of a trapezium. Add the top and the bottom. Yes. Add the top and the bottom. Multiply to find the area, says Christina. Not a math teacher. Even just to find the area, you multiply. To find the perimeter, you add. Should finding the area and finding a perimeter be taught together? One is addition, one is multiplication. I'm loving the difference in people's schemes of work at the moment when I visit schools, because some are adamant they go together, but they're completely separate subjects. Now, I think there are arguments for both ways here, but I do know plenty of people who will not teach them anywhere near to each other, because one is multiplication and one is addition. Let's see the point that she makes. So a rectangle with length 5 and breadth 2 has area of 5 by 5 by 2 by 2, and perimeter 5 plus 5 plus 2 plus 2. Difficult to know what to do. Certainly with this expression used, that's the misconception that pupils might just make. Representation, by the way, does a really good job in getting rid of that. Rob, great guy. Rob, do the brackets. What do you mean do? Do the brackets. What mathematical language is that? Do the brackets first. I don't know. Always? So you said do the brackets first. Do we do it always first, do we? Well, let's find out. Let's solve this equation here. 3 lots of x plus 1 equals 15. Do we always do? Do you mean expand? Do the brackets first? Well, look at these two. Got Mullen and Mamie's equations solving here. They have both solved the same equation. And they've both got it right. Do we have to expand the brackets first? Now, I've taken this from my favorite book at the moment, Making Every Math Lesson Count. And just saying, well, you've got to expand the brackets. Well, hold on a second. You're losing a great opportunity to make connections. Look, even comparing those two solutions there, those two methods, what's the same? What's different? What do you notice? Where is it? Where's the 1 disappeared on the left-hand side? Oh, yes, because you had to multiply by 3. We're making those connections. We're practicing more and more about the expanding of brackets. But which is more efficient? Is it always better? Because look how many steps Mamie's solution. It only took 2 steps. Oh, in which case, divide by the brackets always. That's much easier, isn't it? But what about if it had equal 14? Would that have been as good? Look at the mathematical conversations you can do. Do the brackets first. Yuck. Certainly not. So that's a worked example taken from this fabulous book, Making Every Math Lesson Count. And worked examples are one of the most effective ways to reduce cognitive load. I'm going to be looking at those in a session in a couple of weeks' time. I'm really looking forward to the session in a couple of weeks' time. Oh, I've got a good one coming, but I'm not going to tell you now. There's a great chapter in Making Every Math Lesson Count, beautifully called Speak Proper. Plug in the 2 or put 2 in when substituting numbers in algebra. So there's a risk that students will be unfamiliar with the formal language of maths. Substitute 2 for x. Adam, just want to check. You haven't interrupted me once. Are we okay?
We're absolutely fine. I think lots of people are answering each other's questions in the chat. So if you want to get involved in the discussion regarding anything that Tom's saying, I would recommend having a little look at the chat.
Nice one. Thank you, Adam. I just realised, what time have I got to? Wow, 55 minutes of non-stop. Bring it on. And I'm not slowing down yet, people. All right, let's carry on. So let's speak proper. Let's speak proper a little bit more. Top number and bottom number describe parts of a fraction. Well, what's wrong with that? It suggests that the numerator and denominator are separate numbers, where in fact the fraction is itself one number. I talked about that a little bit earlier on, didn't I? So let's use the terms numerator and denominator. Let's do it right. Stating that a number divides evenly into another number. That's interesting. 5 divides evenly into 45. And by the way, I'm not going to pretend I'm on an incredibly high horse here and say that I haven't done these things or I don't sometimes let these things come out. Of course it happens. But that's the point of today, challenging ourselves to think about it. 5 divides evenly into 45. Well, the word even has a different meaning. And so therefore it's being misused. How about if we say 5 is a factor of 45? That's nice. 45 can be divided by 5 without remainder. Isn't that nice? And I would have said, I hold my hands up here, I'd have said evenly. But there, oh, I've written 5 as a factor of 5. Oh, I knew I'd find a mistake on here. 5 is a factor of 45, of course. Made a mistake. Ooh, fruit salad algebra. A is for apples. This embeds the misconception that a letter represents an object rather than a variable. When we're introducing algebra, this is a really key moment. A key moment. That letter, it's not a letter, we're using a variable. It varies in its value. Such a key moment. And if you go for A's for apples, you're making them think it's an object as opposed to a variable. So why not say let A be the number of apples in a bag? Therefore 3A is then the 3 bags of apples. Or A is the unknown length. It's an unknown, a variable. It's unknown currently, yet. All of those taken from that fabulous book from Emma McRae. I don't mind promoting it because it's brilliant. What we got next? Sean Powell works over in Inspiration Trust in Norwich. Follow him on Twitter. Wowee, some of the stuff he shares. Take out 2 from the bracket. Take out 2 from the is that what I do? Do I take out the 2? Oh, you mean take 2 from the left? You take what? Do we mean factorize? Then say factorize. You can never cross an asymptote. This needs to go away, says Chris. I love that passion, Chris. Thank you. So there's a graph there, and the asymptote, I believe, is at x equals 3. But doesn't the x-axis cross the asymptote? So can you cross an asymptote? Should we say the graph won't cross the asymptote? When subtracting, the biggest number goes on top. We've already had that, Mark. And Jason, we've had that as well. But hold on. Thank you both for this, because what are you linking me to? More research. 12 math rules. Maths. It's American. Fine. Okay. 12 math rules that expire in the middle grades. Okay. So Randy, he said that there's 13 rules that expire. And there's stuff we're teaching them that later on is no longer true. So I thought I'd look these up. I've been linked to some really good papers here. And that's why I'm so thankful for the people who responded to my tweet, because it really opened my eyes to some of the stuff out there. In this article, we present 12 persistent rules that expire. These are rules that we have found prevalent in our many years of working with students from maths education literature, or in some cases, rules that we have ourselves taught and later regretted. You can't have more than 100% of something. Yes, you can. Just that's it. Yes, you can. There's some alternative here, and like the book in the Emma McRae book, some things that people have said. Using this, so read this carefully with me if you would. 8 plus 4 equals 12 plus 5 equals 17 plus 3 equals 20. As teachers, sometimes we make that mistake, but what a difference it should be. That equals sign is not the solution. It's what's on the left-hand side of the equals is the same as the right-hand side. And 8 plus 4 does not equal 12 plus 5, and it doesn't equal 17 plus 3. Yes, 17 plus 3 equals 20, but that is not true. We have to be careful if we're saying the right stuff. Here's one I hadn't thought of until I saw this paper. Using point to read a decimal, such as 3.4. Okay. Instead, read a decimal as a fraction. 3.4 is 3 4/10. This will make converting decimals into fractions an easier task. Use the word point only when describing how a decimal is written or in a geometric context. That is interesting. And again, I said it at the very beginning, I want you just to think about stuff today and some ideas, and that one really got me thinking. I referred to this earlier on, reducing fractions. If we reduce a fraction, it makes it sound like its value is getting smaller. If we simplify a fraction, 2/6 equals 1/3. We haven't reduced it, we've simplified it into its lowest terms. Chorna Warner, what a great Twitter name. I'm constantly correcting myself when I say number rather than digit. Now, it was a primary specialist who first made me think about this properly. Let's look at this. Can you look at the bottom for me first? This thing here, it woofs, it's got a collar on, it tail wags, and when it's happy, it barks at you. It's a thing. The word we use to describe that thing is dog, and we break it up using 3 letters, D-O-G. This is the number of counters you can see here. You can see 153 counters. The numeral that represents the number of counters is this. And we use 3 digits, 1, 5, and 3, to create the numeral that represents the number. Wow! How often do we say number all the time, where we could be breaking it into these 3 categories, and rightly so? How interesting. Again, I found doing this fascinating. All the pedantry here is fascinating. So why do maths teachers still talk about objects having weight in kilograms? That's maths, people! Weight is measured in newtons. And if we're going to be pedantic, well, let's point out the fact that you've put a apostrophe in the wrong place. But of course, the sign is an equivocal Esquire is completely correct. I'll just give you a chance to read that little image at the bottom. I've regularly had that on my wall over the years. Weight is measured in newtons. They're right. That tweet's right, you know. So I mentioned Maths, Mr. McGordon. We're getting very close to the end now, actually. We're going to finish early today. Yes, Ben sent this great tweet, and he'd read a blog from Danny Quinn. She's the head of maths at Michaela, and Michaela, one of the most famous schools in the country, one I very much want to visit. And he created a visual summary of her fantastic blog, and we're going to look at it very quickly now. So there was the visual summary. I'm going to break it down and talk through each bit of it in a moment. But it's increasing rigor, the making sure the words we use and the words we expect of our pupils in the classroom. Talking in general terms, a lot of the explanations we give to pupils focus too much on the specific example. So just looking at this middle one here, if you would with me, to get the perimeter, add 6 and 7 and 6 and 7, and don't forget for units, but that's referring to this example and this example alone. What an interesting twist to it. To get the perimeter, I need to add the lengths around the outside. Some of them are blank, I'm going to fill them in. But it's not just saying, how do you find the rectangle's perimeter? 7 plus 6, 7 plus 6. How about length plus width, length plus width? How about the lengths on the outside? Just getting people to generalize what they're doing, really interesting. Clamp down on pronouns. So the more often you use them, use pronouns so that they usually say it's, they, and them. Well, let's do better than that. You multiply them. How about multiply the base and the perpendicular height? Although, of course, you had a bit of an argument over that earlier on. You find its height to find the slant height of the parallelogram. So perpendicular. You add them and divide by how many there are. Add the values and divide by the number of values. So do we just say them, it? Do we say that too often, or do we make them use the proper language? Really interesting. Use elaborative interrogation. A lot of the questions in math class students have a 50-50 chance of being correct, which means, well, especially considering that our body language often conspires to give away. So is it this one? Or that? Are these lines parallel, or how do you know these lines? Look at that for a really good question. Are these lines parallel? Yes, thank you. How do you know they're parallel? Which number should I use for height? 8 or 6? How do you know and why? Elaborative interrogation, really good thoughts there. And help them to build expectations as well. Make sure that pupils have some expectations around the answer before they get started. For example, I should read this, sorry. Similarly, teach them to use words in the question to begin visualizing or imagining things. The middle one here, if I sketch the circle and the straight line, I can see where they might intersect. One of the angles in the triangle is 80, so therefore, my answer must be less than 80. I didn't do this one here, and I talked about estimation briefly earlier on. It is an enlargement of a negative scale factor. It'll be drawn somewhere here. If you know it's negative, you know it's going to be the other side of the center of enlargement. And even just having that estimation, that understanding, what a great opportunity to help children to feel familiar with the process and to move to expectations. From this book, so communicating mathematically. I'm going to take a quote from it, if I may. The conciseness and precision of mathematical notation, vocabulary, definition, and argument are not merely conventional. They play important roles in mathematical thinking. There is, however, tension between the wish to introduce students to conventional mathematical means of communication and the need to avoid mystification and consequent anxiety. And in this book, when it's got that, the following paragraph says, discuss it with your colleagues. Should we use the right language? Shouldn't we use the right language? Have that professional collaboration. And one of the most powerful things we can do as teachers is work together and be discussing with your colleagues. What do you do? Why do you do it? Why do you find that more powerful? Finding out from your feeder schools what they do. Feeder schools finding out what the secondary schools want to do. And so the question here is, there's tension between, do we teach them the right words or do we teach them some tricks? Now, I'm going to have to quote my favorite artist of all time here. Because if you're going to do it right. Surely you've got to do it right, people. Because if we all do it right, we're all going to be consistent. Surely it's low expectations if we say top and bottom when it comes to numerator and denominator. Surely we're saying, oh, they can't understand those things. So you're setting those boundaries for those kids, saying they can't learn that. Really? You've got pupils in your classroom, you're turning around to and saying, you can't learn that, so I'm going to cheat it for you. I'm going to trick it for you. If that is the way you're approaching lessons, ask yourself, are you being fair by that child? You're not setting high expectations if you're setting those tricks, if you're using the language. Now, again, the argument's going to come back, and I agree with it to a certain degree. Year 11, it's spring. The exam's in a few weeks. Am I worried right then? I'm probably going to go down the tricks route. That's a fault of the system. But for the mathematics, if we want them to do it, surely if they're going to do it, we get them to do it right. Love you, George. And there we go, we got to the end. So I'm going to share all those links in a moment. Thank you for tuning in. That's my Twitter handle. Please, if you've actually enjoyed it, share it on Twitter. Share the good vibes. I'm doing it all for free because it's fun and I'm enjoying myself. If you've got any questions, queries, complaints, or thoughts, please do email me as well, or do tweet me. There's my email address. I think there's a couple of things I want to point out before we go. Think before you speak. Breathe before you think. What is the language I've got to use moving forward? My previous sessions can be found on YouTube. I've talked about representation and the integers one. I really enjoyed doing that. My next session, ta-da! Next week, next Friday, bar modelling, an introduction for secondary teachers. Going to use some quiz and air rods as well. Key stage 3, key stage 2 as well. I've written key stage 3 mostly, but I think key stage 2 will be interested. And key stage 4 hopefully as well. So I'll be doing that session next week. The one in 2 weeks time as well I'm looking forward to, but I'm going to keep doing these. I hope you've enjoyed it. I hope you found it interesting. I'll stick around for any questions. But I hope that was challenging. And if it just makes you think about the language you use in the classroom, then the last 70 or 80 minutes will have definitely been worth it. So thank you very much for your time today. Stay safe, enjoy the bank holiday, and keep washing those hands, people. Thank you for so many people tuning in. I'm touched.